Welcome to lab number 11, which is major project checkoff number 3. In this lab, we will record all of the electrical resistance and capacitance values that are analogous to the fluid resistance and compliance values of the major project. We will enter 2 of them into a model of the left ventricle, also called a capacitance multiplier circuit. We will simulate then an isolated beating heart, and from the results of that, we will investigate 2 findings.
Now here's a list of the items that we need to check off for checkoff number 3 in this week's lab. This list came from a list that's in the appendix of the textbook. It's a little bit different this unusual year. We'll start with filling in table C6, and that table is found at the top of the second of the worksheets for this week's lab, right here. Incidentally, if you're using a blank sheet of paper to provide your worksheets, please use a ruler to make this table and put it on the top of the second page. You don't need to repeat anything in the blue here, just repeat the things in the black. Now, the leftmost column already lists all the fluid quantities from the MATLAB portion of the major project, along with their symbols and their units. You are to fill out the corresponding electrical quantity that's analogous to each of these fluid quantities here. Here are actually the symbols for the electrical quantities, and then fill in the electrical units. You will find that the second half of chapter 11 in the textbook will be very helpful to fill out this table here. Going on, we next need to calculate all of the electrical R and C values. You've started this in your homework last week, but let's review some of the aspects of this. Here is the table we need to fill out. Over on the leftmost column, put in all the fluid compliance values that you got for the MATLAB program and that were listed in lab number 6, which was checkoff 1. Put those values here of the fluid compliance values. And then we need to find the scale factor, S sub C, that we're going to multiply all of those compliance values to get the electrical capacitance values. The way we find that scale factor is we let the scale factor from this equation be determined by our very largest compliance, which I'm pretty sure is the compliance in your veins. So put your value in here. And then we multiply that by a scale factor yet to be determined and set that equal to 100 microfarads. Solve for the scale factor and put it in here along with units in farads will be one of those units. And then multiply each of your fluid compliance values by that scale factor to get your electrical capacitance values in units of farads. Now you'll find that these values are all over the map. They will be numbers that will be some of the numbers of the positive integers. And of course, let's get real. We know that a realistic electronics lab would not have capacitors that would match every one of these values exactly. So let's consider that we're in an electronics lab that has these available capacitor values right here. And this is a worksheet that was passed out. You don't need to turn this in. Use that worksheet to find the closest available value from the available values in the lab and mark that down in this column here. If your capacitance value is very close to one that's available, put that one down here. If it's somewhere in between 2 values, if you round up for this capacitor value, available capacitor value, why don't you round down in the next one, and that rounding will sort of average out as you go down this list. Fill this in all the way down to this point, but do not fill in this square right here. We'll come back to that in a few minutes. We'll also come back to the center section of this first worksheet and fill that out in a few minutes. Go down to the bottom of this first worksheet, and we will do the same thing for resistors. We will take our fluid resistance values, which come from lab number 6, which is checkoff number 1, put those down here, and then we need to multiply all of those by the scale factor for changing fluid resistances to electrical resistances, S sub R. Well, that's now given to us because S sub R is just the inverse of S sub C from the top of this sheet. That's to keep the time constants constant between the electrical world and the fluid world. Put that value down in here along with units. Now, there may be some confusion with units here because the units for S sub R are going to have farads in them. And you say, well, farads aren't anything to do with ohms, but there is an equivalent units equation here. Notice that tau is given by resistance times capacitance, and the units of tau are seconds. The units of resistance are ohms, and the units of capacitance are farads. So a second is equivalent to an ohms farad, or to put it another way around, a farad is a second divided by ohms. Use that equivalent units to convert your S sub R over to ohms, and then multiply using that S sub R all of your fluid resistance values by that S sub R to get your electrical resistance values in ohms right here. But once again, those values are going to be all over the map, and to be realistic, let's assume we're in an electronics lab that only has these resistors here in kiloohms or even megohms here. Find the closest one to your determined values, calculated values here, and put those closest available values in this column right here. And actually, if you have to round, I would round down on each of these because it's going to give you a little bit better cardiac output. Now, going on to our next item, we want to consider the left ventricular module. We'll do that next. Well, here's the left ventricular module as it fits together with the entire circuit for the systemic cardiovascular system that we'll deal with in checkoff number 4. And a little history in the development of this left ventricular module. When I first put together this circuit, I thought it would be easy to represent the heart, the left ventricle, with a voltage source that went between a high voltage during systole and a low voltage during diastole. Because after all, the pressure in the heart, P sub H here in the blue, is high during systole and very low during diastole. And since the pressure and voltage are analogous pairs, I thought putting together a voltage generator that did this would represent the heart. It was a disaster. It didn't work at all. The circuit was very unstable. The blood volume was not conserved, and Starling's law was not met. And here's the reason why. I realized that the heart is not a pressure pump. It is a compliance pump, changing its compliance between systole and diastole. And the pressure change is simply a consequence of the compliance change. So then I went to an idea of using 2 different capacitors, a very big one for diastole and a very small capacitor or small compliance during systole, and switching back and forth between the 2 of them. But that didn't work well either. The reason is that when you switch from one capacitor to the other, the charge on the first capacitor, which represents blood volume, is set aside, and blood volume is not conserved when you go between those 2 capacitors. And so I was at a standstill at that point until I ran across a capacitance multiplier circuit shown here. And this capacitance multiplier circuit allows one to use a single capacitor, one capacitor, C1, and have it switch effectively between 2 capacitance values depending upon the setting of this switch right here. That switch is driven by a pacemaker, and during the systolic time, the switch is down here. So let me briefly describe how this capacitive multiplier circuit works. It looks rather complicated, but it works, and it provides us a way to use a single capacitor to represent the heart. During the systolic portion of the pacemaker, when the switch is down, this lower line here, which is connected to the bottom plate of the capacitor C1, is exactly at ground at 0 volts, the same as this point right here. And therefore, the rest of the circuit that will be attached later to this left ventricular module at point X up here sees the capacitance as exactly C1. But during diastole, when the switch is up, the voltage at the top of the capacitor passes through this voltage follower and is connected to the input of this inverting amplifier that has a gain of negative R2 over R1. The reason we use a voltage follower is to avoid taking any charge off the top of that capacitor in measuring its voltage. What that inverting amplifier does is it takes this lower line now and takes it to a voltage below ground. It is not ground anymore, and it takes it to a voltage below ground. And that drops down the voltage at the lower plate, thereby dropping down the voltage at the upper plate of the capacitor. And when the voltage drops down, that effective new voltage that the rest of the circuit sees at this point means that the rest of the circuit thinks that this capacitor has a much larger effective capacitance. Why? Look at this equation 11.5 from the textbook. If you solve for the effective capacitance, it's the value of Q, which hasn't changed, the charge doesn't change, divided by the effective voltage. If the effective voltage is very low now, it makes the effective capacitance look very large. And that's what we want to represent the diastolic compliance, a very large compliance. Now let's find an equation which relates the values of all of these variables to each other. You are to find the value of C1 and the value of R2 for your particular left ventricular module. R1 is given to you as 10 kiloohms. Well, if you were to do a Kirchhoff's tour around this circuit, I won't ask you to do that, but if you were to do that, you would find that the effective capacitance as seen by the rest of the circuit that we will attach here in checkoff number 4 is given by an equation that the effective capacitance is 1 plus the ratio of R2 divided by R1 primed multiplied by C1. Now R1 primed is the effective resistance between this point here and the input to the inverting amplifier. During diastole, when the switch is up, that's just exactly equal to R1, or 10 kiloohms. But during systole, when the switch is down, that opens up the circuit here, and the effective resistance between this point and the input to the inverting amplifier is infinity. Let's see how that's going to help us to solve for C1 and R2. We'll go back to the middle portion of the first worksheet, return to that, and notice that the equation is repeated here. And during systole, we want the effective capacitance to be the electrical capacitance during systole, or CHS, which comes from this box right here. You put that on the left, and you enter in the fact that during systole, R1 prime, since it's open up, is equal to infinity, and R2 over infinity is 0. So the effective capacitance is just C1. That means that C1 is equal to CHS that comes from this box right here. Put that value in there. The available value, of course, will be obtained off of the sheet of available values. You can put that value right in there for C1. For R2, we go into diastole, and there, the left-hand side of this equation should be the compliance, the capacitance, during diastole, which is CHD, which comes from this box there. Put that on the left side. R1 primed during diastole, when the switch is up, is 10 kiloohms. So put 10 kiloohms in for R1 primed and solve for R2, knowing that C1 was just found a second ago from systole. And solve for R2 and put the R2 value right here, and then find the closest available value and enter that in there. And now that we've found a value for C1 and a value for R2, we can put those values into the simulation, which we will do next. Now, to complete the last task on this checklist, let's look at the left ventricular module and get a color plot of the voltage waveforms. To do so, go to the second sheet of the worksheets near the middle, and we're going to simulate the left ventricle with a capacitance multiplier circuit. So download the file lv1.slx from Canvas, open it up in Simscape, you've done that before, and then set the values of C1 and also R2 to those values that were calculated just a minute ago on the previous page, and then run the simulation. Now when you open up the model in Simscape, you'll see a window that looks like this. This shows our capacitive multiplier circuit that represents the left ventricle, and it's identical to the schematic you saw earlier with one addition. Here's the capacitance C1, resistor R1, and resistor R2. The function generator is the pacemaker which drives this analog switch, and during the 250 millisecond systolic time, the switch is down. During the 550 millisecond diastolic time, the switch is up. What's been added that we need to measure the voltage at C1, which represents the pressure in the heart, and we do that with a voltage sensor which sends the waveform of the pressure in the heart to channel 1 on the oscilloscope. Channel 2 on the oscilloscope is just monitoring the pacemaker voltage here. Before we do the simulation though, you have to change the value of C1 from its initial value to the value that you calculated on the front worksheet. Do that by changing this capacitance from its initial value over to your value. Click OK to save that. I won't do that, I'll keep it at the initial values. Go to resistor R2, click on that and change this value to the value that you calculated on the first worksheet for R2. Click OK and change that. I won't, I'll keep it at their initial values. And then to run a simulation, go up in the simulation tab and click on Run. And in a couple of seconds, the simulation is done. Click on the oscilloscope, double click on the oscilloscope to see the two waveforms, and here they are. The pacemaker waveform is in the blue, and as expected, it goes between 0 and 7 volts every 250 and every 550 milliseconds. In the green is the voltage across the capacitor, which represents the pressure in the heart. It's analogous to the pressure in the heart. Now, to see how close this comes to physiological reality, we need to measure the voltage at the peak of systole and at the dip in diastole here. So, using cursor number 1, we will measure the voltage at the lowest point, which is diastole here, and over in the measurements we can see the voltage, but we want to correspond that to pressure, knowing that 4 volts of voltage is equivalent to 100 millimeters of mercury. You can transcribe this voltage over to pressure in the heart during diastole in millimeters of mercury. Record that on the second page of the worksheets. Then do the same thing for systole. At the peak of systole here, find the voltage using cursor number 2, measure it here, over to the right, and then translate that, knowing 4 volts is equivalent to 100 millimeters of mercury, translate that over to the equivalent systolic pressure in the heart, and record that in units of millimeters of mercury. And then, using our familiar equation that the compliance is equal to volume divided by pressure, and here the volume is constant because it's not going anywhere. This is an isolated left ventricle. Find the ratio of the compliance of the heart during diastole to the compliance of the heart during systole. Find that ratio. That ratio should be 15 or even greater for a good strong heart. See how strong your heart is by calculating that ratio. And then next, let's see if we can calculate the time constant of this circuit here. That represents the 4.7 microfarad time constant along with these 2 resistors to allow an exponential rise and fall of the compliance. So we need to find the time constant. Notice that this 4.7 microfarads capacitor is connected to resistor R2 and also resistor R1 in this configuration here. Using your knowledge of how to combine resistors, find the time constant for this circuit. And incidentally, there's only one, unfortunately, not two time constants. Find the time constant for this circuit and put that down in seconds. And then looking at that value, see if you can see why 4.7 microfarads was chosen as the value for this capacitor. And then to finish up the lab, we need to submit a PDF figure that has these traces as part of the submission along with the two worksheets. To do so, we will do as before, print these traces to the figure window in MATLAB, because the figure window in MATLAB is much more flexible than the oscilloscope window. For example, like before, we can insert a new title here and make it more descriptive. For example, it could be something like left ventricle, or whatever title you might want to put there. But even more than that, notice that the legend is quite small here, and we'd like to identify which of these two waveforms is the pacemaker and which one it represents the pressure in the heart. So let's insert a text arrow and point the text arrow towards the pacemaker voltage and label it pacemaker, P-A-C-E, maker. There, well, it's really a small font. We'll take care of that in a second. Insert another text arrow pointing towards the voltage which represents the pressure in the heart and label that as PH. Now, to correct the font size, we can go even farther in the figure window over here to the Edit tab and edit the axes properties. And up comes a property inspector. Move that off to the side. Double-click on the pacemaker label, and you notice that the font size over here in the property inspector is only 10 font size. Let's increase that to 16, a font size of 16. Click on that, and suddenly the pacemaker is more legible. Click on P sub H, and in the property inspector, increase its font size to 16. And now that's a lot more legible. And this is the figure that we want to submit as a PDF file. To do so, as before, instead of directly saving as a PDF and losing the input and the output of the figure, let's save this as an EPS file, a .EPS file, right here. Let's label it, give it a title of something like left ventricle or LV, and save that to some place where you can find it. I'll save it to Lab 11 here to save that. And then in Lab 11, when we open up Lab 11 and find that LV EPS. And when we open that up in Preview in the Macintosh, it will save as a PDF file, which you then submit along with your worksheets to finish this week's lab. If you're on a Windows machine, you may have to open it up with Adobe Acrobat in order to change it into a PDF file to save it as a PDF file.
Well, I hope you found this week's lab useful in describing how we simulate the left ventricle in our model. It will become a key component when we model the entire systemic cardiovascular system in next lab.